The most popular explanation for ADHD on the internet is wrong. ADHD brains have low dopamine. You've seen it everywhere, from TikTok to therapy waiting rooms. It's simple, it makes intuitive sense, and it's backed by the fact that stimulant medications, which boost dopamine, actually work. But here's the problem. Research shows that ADHD involves complex patterns of dopamine dysfunction, not simply having too little of this neurotransmitter. The real story isn't about having too little of one chemical. It's about a transportation system that works too fast, a prefrontal cortex that can't stay online, and a brain that runs on interest instead of importance. Hey there, neurospicy folks! I'm Dr. Monty, and I'm an ADHD psychologist with a special interest in all things neurodivergent neuroscience. If you enjoy my videos, please consider subscribing to my channel to help me grow and bring more scientific understanding and awareness to a larger audience. Thanks so much! Let me start by validating what you probably already believe, because the low dopamine explanation is seductive for good reasons. When Jan Havik, a neuroscientist at the University of Bergen, was at a routine ADHD research meeting a few years ago, someone with ADHD told him, "As everybody knows, we who live with ADHD have very low dopamine levels." Havik was surprised, not because the person was being presumptuous, but because this idea, while containing a grain of truth, misses the actual mechanism entirely. The low dopamine theory emerged through backwards reasoning that seemed perfectly logical. Starting in the 1930s with the accidental discovery that stimulants could help children focus, and later as researchers began understanding how these medications work, they discovered that drugs like Ritalin and Adderall, which increased dopamine availability in the brain, dramatically improved ADHD symptoms. The logic was simple. If boosting dopamine fixes the problem, then the problem must be not enough dopamine. As James Swanson at UC Irvine puts it, the drug corrects the symptoms, so the assumption is that patients have a deficit of neurotransmitters. This explanation stuck because it maps onto lived experience in ways that feel obvious. You can't focus on boring tasks. Must be low dopamine. You hyperfocus on video games for 6 hours straight. Must be chasing dopamine. You feel unmotivated until a deadline creates urgency. Clearly, your dopamine system needs extra stimulation to function. The narrative writes itself, and it's been amplified across social media, self-help books, and even some clinical settings. But here's where the seductive simplicity becomes a problem. When you measure actual dopamine levels and activity in ADHD brains using advanced imaging techniques, you don't find a straightforward deficit. The real issue isn't the amount of dopamine, it's what happens to dopamine once it's released, how efficiently it communicates between neurons, and how different brain regions coordinate their dopamine-dependent functions. To understand what's actually happening, imagine dopamine not as fuel in a gas tank, but as messages being passed between workers in a factory. In a typical brain, when dopamine is released into the space between neurons, the synaptic cleft, it has time to bind to receptors and deliver its message before being cleared away by transporter proteins. Think of these transporters as efficient janitors who clean up after the message has been delivered. Now here's the crucial finding. Research by Nora Volkow and colleagues has used PET imaging to discover that many adults with ADHD have increased activity of dopamine transporters in key brain regions, particularly the striatum. These aren't lazy janitors, they're hyper-efficient ones. They clear away the dopamine messages before the receiving neurons have had adequate time to process them. Picture this more concretely. In a typical brain, dopamine gets released, binds to receptors, delivers its message about reward, motivation, or attention, and then gets cleared away. But in many ADHD brains, those transporter proteins are working overtime. They're grabbing the dopamine and whisking it away more quickly than optimal. The message gets cut short, even though the same amount of dopamine was initially released. This explains something that the simple low dopamine model struggles with. Why people with ADHD can hyperfocus intensely on certain activities while struggling with routine tasks. When something is genuinely engaging, a video game, a passionate conversation, a creative project, the dopamine release is so robust and sustained that even the hyperactive transporters can't clear it all away fast enough. The signal finally gets through. But for routine tasks that generate only modest dopamine release, those overactive transporters create what researchers call dopaminergic hypofunctioning. Not because there's less dopamine, but because the communication system is too efficient for its own good. The situation becomes more complex when we look at specific brain regions. The prefrontal cortex, which handles executive functions like planning and impulse control, is particularly vulnerable to this transporter problem. Joshua Burke at UC San Francisco describes dopamine in certain structures as closely linked to the decision to engage in a task or identify it as worthwhile, or to be disengaged and do something else. When dopamine signals in the prefrontal cortex get cut short by overactive transporters, the brain essentially decides that whatever you're trying to focus on isn't worth the effort. Meanwhile, in reward processing regions, like the nucleus accumbens, the same transporter issue creates what researchers call reward deficiency syndrome. It's not that people with ADHD don't experience pleasure, it's that they need more intense or novel stimulation to generate dopamine signals strong enough to overcome the hyperactive cleanup crew. But dopamine isn't working alone. Norepinephrine, dopamine's chemical cousin, is also important in ADHD. Both neurotransmitters are cleared by some of the same transporter proteins, and both are boosted by ADHD medications. This is why the most effective ADHD treatments, like Adderall, target both dopamine and norepinephrine pathways simultaneously. There's also a genetic component that makes this picture even more precise. Variations in genes like DAT1, which affects dopamine transporter function, can influence how efficiently dopamine signals work in the brain, contributing to some of the differences seen in ADHD. Research has shown that people with certain genetic profiles may respond differently to ADHD medications, suggesting that their brains have distinct patterns of dopamine transport efficiency. Now let's complicate this picture, because the brain is never as tidy as any single explanation suggests. While the transporter hypothesis explains a lot, it doesn't explain everything, and recent research has revealed some important contradictions and gaps. The replication challenge comes first. While Volkow's original findings about increased transporter activity have been replicated in several studies, the effect sizes vary considerably, and some research has failed to find the same patterns. A 2019 meta-analysis by Haley McDonald and colleagues at the University of Bergen found that while dopamine dysfunction is clearly involved in ADHD, the specific mechanisms vary more than initially thought. Some people with ADHD show the classic high transporter pattern, others show receptor differences, and still others show variations in dopamine synthesis or metabolism. This variability might explain why ADHD presents so differently across individuals. The inattentive type, the hyperactive impulsive type, and the combined type might actually represent different underlying dopamine dysfunctions. Someone whose ADHD primarily involves attention problems might have transporter issues mainly in prefrontal regions, while someone whose ADHD is primarily hyperactive might have different patterns in motor control circuits. There's also the developmental complexity. Brain imaging studies in children with ADHD show that the cortex in attention control regions is measurably thinner than in typical children, but this difference often normalizes by adulthood. This suggests that ADHD might involve developmental delays in dopamine-dependent brain circuits, not permanent deficits. Some researchers now think of ADHD as developmental dopaminergic dysregulation, a timing problem in brain maturation rather than a fixed chemical imbalance. The clinical populations reveal even more complexity. People with ADHD and comorbid conditions like autism or anxiety show different dopamine patterns than those with ADHD alone. And here's something particularly interesting. Some individuals with ADHD show completely normal dopamine transporter density, but have differences in receptor sensitivity instead. Their transporters work fine, but their receiving equipment is miscalibrated. Then there's the medication paradox that researchers are still trying to fully explain. Stimulant medications work for about 70% of people with ADHD, but 30% don't respond or respond better to non-stimulant treatments that work on entirely different neurotransmitter systems. This suggests that ADHD might actually be several different conditions that produce similar behavioral symptoms through different biological pathways. Recent genetic studies have identified dozens of different gene variants associated with ADHD risk, and only some of them involve dopamine pathways directly. Others affect brain development, neural connectivity, or entirely different neurotransmitter systems. This polygenic complexity means that while dopamine dysfunction is clearly central to many cases of ADHD, it's not the whole story for everyone. We also don't fully understand why the transporter overactivity develops in the first place. Is it a direct genetic effect, a response to early environmental factors, or some interaction between genes and experience? The research is still emerging, and honest scientists will tell you that the causal chain from genes to transporters to symptoms remains partially mysterious. So what does this more accurate understanding mean for how you think about ADHD, whether you have it yourself or know someone who does? This reframes the entire experience from a deficit model to a mismatch model. ADHD brains aren't broken or lacking something essential. They're optimized for a different kind of environment. The hyperactive dopamine transporters that create problems in modern classrooms and offices might have been advantageous in environments that required rapid shifts of attention, quick responses to changing threats or opportunities, or sustained focus on genuinely engaging activities. This has practical implications for how you approach focus and productivity. Instead of trying to force your brain to care about inherently unrewarding tasks through willpower alone, you can work with your dopamine system's actual requirements. This might mean breaking large projects into smaller chunks that provide more frequent reward signals, or deliberately pairing boring tasks with genuinely engaging elements. Understanding the transporter mechanism also explains why environmental modifications often work as well as medication. Reducing distractions doesn't just help you focus, it reduces the competing dopamine signals that your hyperactive transporters are trying to clear away. Creating external structure and deadlines doesn't just impose discipline, it generates the urgency-based dopamine release that can finally overwhelm your over-efficient cleanup system. The research on individual variation suggests that ADHD treatment should be more personalized than it currently is. If your ADHD involves primarily transporter issues, stimulant medications that block those transporters make perfect sense. But if your ADHD involves receptor sensitivity or developmental timing issues, you might respond better to different approaches entirely. This is why some people thrive on stimulants while others do better with therapy, exercise, meditation, or environmental changes. Perhaps most importantly, this understanding can change your relationship with your own brain. The experience of being unable to focus on important but boring tasks isn't a character flaw or a lack of discipline. It's a predictable result of having dopamine messages that get cut short before they can properly motivate sustained attention. The ability to hyperfocus on engaging activities isn't compensation or procrastination. It's your brain working exactly as it's designed to, just under conditions that generate sufficient dopamine to overcome your transport system's efficiency. This also means that the popular concept of dopamine detoxes fundamentally misunderstands ADHD neurobiology. Deliberately reducing dopamine stimulation might actually worsen ADHD symptoms by making it even harder for truncated dopamine signals to get through. Instead of detoxing from dopamine, ADHD brains often need more reliable, sustainable sources of dopamine stimulation. The next time someone tells you that ADHD is simply about low dopamine, you can offer them a more accurate picture. ADHD isn't a dopamine deficiency. It's a dopamine communication problem. The brain produces plenty of this crucial neurotransmitter, but hyperactive transporter proteins clear it away before it can properly deliver its messages about motivation, reward, and sustained attention. This explains both the challenges and the contradictions of ADHD, why routine tasks feel impossible while engaging activities become effortlessly absorbing, why stimulant medications help even though they're adding more of a chemical that isn't actually lacking, and why ADHD brains aren't broken, but rather optimized for a different kind of world. Understanding this mechanism doesn't just satisfy scientific curiosity. It opens up more effective, personalized approaches to working with ADHD brains rather than against them.